Okay, so hi everybody, and welcome back. What we're going to be doing today is a continuation of our review of basic thermal physics. This is what we started in the previous video. So by the end of this video, we'll be done with that review. And what we left off with in the last video was a discussion of specific heat. So now we're going to move on to something called latent heat. So I want to introduce this concept by showing you some experimental data. So at the bottom of the screen, you see a graph. And what this graph is showing you is what happens when we take a sample of water, H2O, and gradually add heat to it. So the starting state of this sample is that it's at negative 40 degrees Celsius and it's all solid ice. So the graph on the vertical axis is showing you the temperature of this sample. So the temperature in degrees Celsius is on the vertical axis. And on the horizontal axis is the total amount of heat that we've added to the sample. So let's start down here. This is the starting point of the graph where the sample is at minus 40 degrees Celsius and no heat has been added yet. Okay, so after that, as we add more heat, we increase the temperature of the sample. See how as we add heat, as we go to the right, the temperature goes up, okay? But that only happens for so long. Once we reach a temperature of 0 degrees Celsius, notice how we're still adding more heat, but the temperature isn't increasing, it's just flat. So what's going on here? Well, 0 degrees Celsius is the melting point of water. So what's happening here is this solid ice is melting and becoming liquid water. Okay, and in this region here that I'm highlighting, some of the sample is still solid ice, but some has been turned into liquid water. Okay, but by the time we reach this point over here, it's all been converted to liquid water. Okay, next, we have a sample of completely liquid water. As we add heat to that, as we go to the right, you see the temperature increases, and that just keeps happening. There's a linear increase in temperature until we reach this point right here. And notice that the temperature over here is 100 degrees Celsius. So that, as you know, is the boiling point of water. So now as we add more heat past this point, the temperature remains constant. It remains at 100 degrees Celsius. And what's happening here is, in this region, some of the water is still in the liquid phase, but some of it has been converted to steam. Okay, some of it has already boiled away. And that keeps happening until we reach this point right here. And this is where all of the liquid water has boiled away and now it's all steam. Okay, so then after that, as we add more heat, you see the temperature of that steam is now increasing. Okay, so what's sort of the takeaway point of this graph? Well, we see that when there's no phase change happening, let's say over here, if you add heat, it goes into increasing the temperature of the system, right? The temperature goes up as you add heat. But that's not true when we're undergoing a phase change, like over here. So during a phase change, the temperature remains constant. And that added heat doesn't go into increasing the temperature, but instead it goes into breaking bonds between molecules that allows the substance to change phase. Let's say from liquid water into steam, okay? So temperature remains constant during a phase change. So let's get some definitions down. So when we talk about the latent heat of a system, that's just the energy required to change the phase of the system. So like if I had solid ice, how much heat would be required? How much energy would I have to put into it in order to melt all of it? Or let's say I had some liquid water. How much energy would I have to put in to boil all of it away? That would be the latent heat. Okay, so specific latent heat, and this is given by the variable L, capital L, is the amount of energy that would be required to change the phase of 1 kilogram of the substance. So this time, the question would be, if I had a kilogram of solid ice, let's say, how much energy would it take to melt 1 kilogram of ice? So we're talking about a specific amount of substance, okay? So the SI units here are going to be joules per kilogram, joules divided by kilograms. And so the equation that we have is shown in the middle of the slide. Q is equal to plus or minus M times L. So what is Q? As always, Q is the heat flowing into or out of the system. M is the mass of the substance that's undergoing the phase change, so whatever that happens to be. And L is, again, the specific latent heat of the substance. Okay. Now, why do I say plus or minus? Well, plus means heat is going into the system. So, for instance, you would have, let me just write this on the slide, you'd have positive for melting. So heat would be going into the system in that case. Let's say you were freezing, you would need to remove heat from the system, so you would choose the negative sign. Okay, so that's why you have a positive and a negative sign potentially. And then lastly, as we saw earlier, when there's a phase change happening, the temperature of the system remains constant. That's really important to remember. Okay, so let's do an example. Let's say we have a 50-gram solid ice cube whose temperature is 0 degrees Celsius, so it's at the melting point. We place this ice cube in a microwave with a power output of 1,000 watts. So a watt is a joule per second, if you remember. How long will it take for the microwave to melt the ice cube entirely? So we're going to assume here that all the energy output by the microwave is going into melting the ice cube. And another piece of information we're going to need to know is that for water, the latent heat of fusion is 3.34 times 10 to the 5 joules per kilogram. So when I say the latent heat of fusion, I just mean that's the latent heat associated with melting or freezing of ice. So let's work this one out. Okay, so the first thing we'll note is that if we want to melt the ice cube, heat required to melt the ice cube is going to be given by Q equals plus M times the latent heat of fusion. So I'm choosing the positive sign because energy is flowing into the ice in order to melt it, right? Okay, the next thing we'll take a look at is the power output of the microwave. So P, power, is defined to be the energy transferred per unit time. That's how we think about power. That's the definition. So in this case, the energy transferred is Q, the heat added to the ice cube, and the time, we'll just call that T. But we know that Q is given by the mass of the ice cube times the latent heat of fusion of the water, and then we divide by T. And what I'm trying to do here is figure out T. How long does it take to transfer all that heat and then melt the ice cube as a result? So the time is M times LF divided by P. And let's plug in what we know. The mass of this particular ice cube was 50 grams, so 50.0. If we want to convert that to kilograms, that's 10 to the minus 3 kilograms. The latent heat of fusion was 3.34, 10 to the 5 joules per kilogram. And then we'll divide by the power. So the power output of this microwave was 1,000 watts, but a watt is the same as a joule per second. Let's take a look at our units here. Kilograms cancel, as do the units of joules. And then we're left with units of seconds on the top. If you do the calculation, you get 16.7 seconds. So that's how long it takes to melt the ice cube using this microwave with this power output. So it makes sense. If we were to increase the power output, we would get less time, so it would melt the ice cube faster. And if we were to decrease the power of the microwave, it would be more time, and that means we'd melt the ice cube slower. Okay, so here's another example, and I'd like you guys to try to do this one on your own at home. The question is, how much energy is required to boil away 2.75 kilograms of water which is initially at 10 degrees Celsius. So roughly that's how hot the water would be if it came out of the tap. So for liquid water, the specific heat is 4,186 joules per kilogram per degree Celsius, and the latent heat of vaporization is 2.26 10 to the 6 joules per kilogram. Ignore heat flowing to the container and only consider heat flowing to the water. Okay, so the question is, how much energy, how much heat are we going to have to transfer to this water to boil it all away? See if you can calculate this. So to work this out, the first thing we have to recognize is that the total amount of heat that we need to add to this water to boil it all away is going to come in two parts. So first, we need to add some heat to change the temperature to get the water from 10 degrees Celsius to the boiling point, which is 100 degrees Celsius. So we have Q to change temp, let's say. And then after we get this liquid water to its boiling point, then we have to add some heat to actually boil it away, to undergo a phase change. Okay? And the way we express the heat required to change the temperature is mc delta T. So the mass times the specific heat times the temperature change. For the phase change, we have M times L. And in this case, it's the latent heat of vaporization. So what we get is, I can take the mass and just bring it outside as a common factor, 2.75 kilograms. Then we have C, which is the specific heat of liquid water, 4,186 joules per kilogram per degree Celsius. And then we have the temperature change, which is 100 degrees Celsius to get to the boiling point. That's our final temperature, minus 10 degrees Celsius, which is where we started. And then finally, I'll just add to that the latent heat of vaporization, which is 2.26 10 to the 6 joules per kilogram. Because I took the mass out to the front already. So when you make that calculation, what you get is 7.251 times 10 to the 6 joules. And you can round that to 3 sig figs to get 7.25 times 10 to the 6 joules. So that's almost 10 million joules that would be required to raise the temperature to the boiling point and then boil all of that water away. This is how much energy is going to be needed. Okay, so next, let's talk about isolated systems. This is a very useful concept because it can be used to solve problems involving heat being transferred between many different objects. So the definition of an isolated system is just any system that doesn't exchange energy with its environment. So that means that we don't have any heat flowing in or out of the system. So Q total is equal to 0. And also we don't have any work being done on the system, meaning W external is equal to 0. If you recall, heat and work are the two different ways that energy can flow between a system and its environment, and we're saying those are both 0. That's what it means to be isolated. So to give an example of this, let's consider the system shown in the diagram where we have two objects. Object number 1 is the hotter object, and object number 2 over here is the colder object. So if we draw a little boundary around object number 1 that's shown right here, okay, we know that heat is going to flow out of this boundary because if you put two objects, one of them hotter and one of them colder, we know that heat flows from the hot object to the cold object. So Q1 is negative, meaning heat is flowing out of object number 1. On the other hand, Q2 is positive because heat is flowing into object number 2. But if we draw a boundary around the system as a whole, like this, well, if the system is isolated, that means no heat is flowing in or out of that boundary, okay? So Q total which would be Q1 plus Q2 in this case, should equal 0 because overall no heat is flowing in or out of the system. But in general, what we can say for an isolated system, if we take all the different heat terms for all the different parts of the system, Q1 plus Q2 plus however many terms we need to include everything in the system, that should equal 0. That's what it means to have an isolated system, is that the heat terms for the various objects in the system are going to sum to 0. And conceptually, what that means is if one object loses energy, another object has to gain that same amount of energy because overall no energy is flowing in or out of the system. Okay, so let's keep that concept in mind and do this example problem. So we have a well-insulated container that holds 567 grams of liquid water initially at 20 degrees Celsius. We have a 155 gram sample of aluminum that's placed under a flame and heated to 325 degrees Celsius, and then it's placed in the water. What is the final temperature of the water in the aluminum sample? The specific heats of liquid water and aluminum are 4,186 and 900 joules per kilogram per degree Celsius, respectively. We're going to assume that no energy is lost from the aluminum plus water system during this process. Okay, so let's try to work this out. Okay, so first thing we'll do is write down the fact that our system consists of the water, it's H2O, and the aluminum, Al. And if we draw a picture of our system, imagine we have a container, it's filled with water, and then we've placed this hot aluminum sample in the water. So the system, if we draw a little box around it with a dashed line, is this. That's our system. Just the water and the aluminum together. So we're told that this is an isolated system. So no heat flowing in or out of the system overall. Q total is equal to 0. And as we just learned, that means QH2O plus QAL, the two different heat terms, have to add to 0. Okay, well, for the water, the heat is given by M. Let's actually write MH2O. That's the mass of the water, times CH2O. That's the specific heat of the water, times delta T H2O. So what we can imagine is the water is heating up and its temperature is increasing. At the same time, for the aluminum, we have MAL times CAL, that's the specific heat of aluminum, times delta T AL. So as long as nothing is undergoing a phase change, that's all we need to do to write down the heat. And that is equal to 0, of course. Okay, so now let's put in the numbers that we know. So for the water, the mass is 567 kilograms, 567 grams, which is equivalent to 0.567 kilograms. The specific heat of the water is 4,186 joules per kilogram per degree Celsius. And then what about the temperature change? This is going to be final minus initial. Well, I don't know what T final is, so I'll leave that as a variable. But I do know that for the water, T initial is 20 degrees Celsius. Okay, now the second term in the equation is the mass of the aluminum, which is 155 grams or 0.155 kilograms. The specific heat is 900 joules per kilogram per degree Celsius. Now, then we have delta T for the aluminum, the temperature change for the aluminum. That's final temperature minus initial temperature. Well, the thing is, it has the same T final, and I'm going to write this on the side because it's really important. Same final temperature T final, when equilibrium is reached. So what this means is the aluminum starts off with a much higher temperature than the water, but if you allow them to reach equilibrium, they'll end up with the same final temperature. So TF for the aluminum is the same as TF for the water. It's really important to remember that. And then the initial temperature was 325 degrees Celsius, just like that. And then this is equal to 0. Okay, so that's our equation. It's a really simple algebraic equation where the only unknown variable is TF. So rather than spend any time going through the algebra and showing you the calculation, I trust that you'll be able to do this on your own and then find that TF is equal to 36.9 degrees Celsius. So we use the fact that we have an isolated system and that the total heat for that system is 0 to figure out what the final temperature is going to be. That's one way you can use this idea. So the next thing is modes of heat transfer. So if you remember, in physics, when we use the term heat, given by the variable capital Q, we're referring to a transfer of energy from one place to another due to a temperature difference between those two regions. So the classic example of this is given in the picture below, where you have a hot object and a cold object. Let's say the red block starts off at 300 degrees Celsius and then the blue one starts off at 0 degrees Celsius. If we put those two objects together and we allow them to interact with each other, what's going to happen is heat will flow from the hot object to the cold object. And when that happens, the hotter object, its temperature goes down. The cold object, its temperature increases. And that will continue to happen until we reach thermal equilibrium. Once we reach thermal equilibrium, heat stops flowing and the two objects end up with the same final temperature. So in this case, we're showing them having the same final temperature of 150 degrees Celsius. So that's all true, and that's all important to have in your mind, but some of the details are left out. So the question here is, we know that heat flows, but how does that happen? What is the mechanism by which heat is being transferred from one object to another? That's the question we want to answer. So it turns out there are 3 ways that heat can be transferred, okay? And they're called conduction, convection, and radiation. We're going to talk a little bit about each of these modes of heat transfer right now. Okay, so let's start with conduction. Conduction is a transfer of energy from one place to another because of collisions between molecules. And there's actually no large-scale movement of matter when you have conduction of heat. So to give you an example or a sense of what this looks like, here's an animation that I'll show you. In this animation, on the left side, we have a flame that's being put right next to a solid object, like this. And we can actually see the individual molecules that make up that solid object. Each one is a little ball in this animation. So when you put the flame next to the left side of the object over here, of course, we'll be heating up these molecules, and that will in turn make them jiggle faster, okay? Now these molecules that get heated by the flame are in contact with these molecules immediately to their right. And since these ones are jiggling around, they're going to collide with these molecules, which will make them jiggle around faster. These molecules will collide with the molecules over here, make them jiggle around faster. And you see this just propagates down the line. Because of these collisions, we're transferring energy from the left to the right. That's conduction of heat. So if we take a look at the animation, that's exactly what's happening. So the molecules immediately next to the flame are heated first. They jiggle around faster, collide with the molecules to their right, which then causes them to jiggle faster. And then we see that heat is being transferred down the line from left to right, and that's conduction. So typically in a solid material, conduction is the dominant form of heat transfer. So for example, if you take a cast iron skillet and you put it under a flame, if you put it on your stove, you notice that the handle of that cast iron skillet gets hotter, right? Well, how is it that the handle of the skillet got hotter? It's conduction of heat. All right, so next, let's talk about convection. So in convection, energy is being carried directly by a fluid moving from a high temperature to a low temperature region. So unlike conduction, there is actually a large scale movement of matter from one place to another in convection. So a classic example of this is shown in the animation here. So we have a flame, and imagine we're putting that flame to, let's say, a pot of water. Let's say this is a pot of water up here. So the water immediately under the flame is going to become heated, and it will have a higher temperature initially than the water, let's say, up here that's not directly exposed to the flame. So what's going to happen is water is going to want to move from that high temperature to this lower temperature region, and that will set up what's called a convection current. And when we play the animation, we can see these convection currents. So again, there is a large-scale movement of water happening within these convection currents, so it's not the same thing as conduction. So convection is usually the dominant mode of heat transfer within a liquid or a gas, so air or water. Typically, it's going to be convection that's carrying the heat around. Okay, so lastly, let's talk about radiation. So radiation is a form of heat transfer where the energy is being carried from one place to another through electromagnetic waves. And that's just a fancy term for light. So it turns out light itself carries energy. And when light goes from one place to another, it can transfer energy from one place to another. So the classic example of this, of course, is the energy transferred from the sun to the earth. So this happens through radiation. It doesn't happen through conduction or convection, because if you think about the space in between the sun and the earth, it's pretty much a vacuum. There's almost no matter out there in empty space. So that means, it's not convection that's carrying the energy from the sun to the earth. It's not conduction, because both of those require some kind of material for the energy to move through. In this case, it's just light that's traveling from the sun to the earth. That's what transfers the energy from the sun to the earth. And by the way, we need this to sustain all types of life on Earth. So radiation is a little bit different from the other two, because unlike conduction and convection, you can actually transfer energy through purely empty space, okay, with radiation. So you don't even need any kind of material for the energy to move through. It can happen in perfectly empty space. Okay, so we talked a little bit about modes of heat transfer. We're not really going to get too much into the mathematical details of each one of those. I just wanted to kind of outline them for you, so you at least have a conceptual idea of how heat gets transferred in different situations. So now let's move on to the next topic, which is ideal gases. All right, so the first thing we're going to cover is what are some of the assumptions that we make when we refer to an ideal gas. What makes something an ideal gas? So first, an ideal gas consists of a really large number of molecules that move in random directions with some range of speeds. So what that means is there's no preferred direction of their motion. It's not like they're moving more in the X direction than they're moving in the Y direction. There's just no preferred direction for their motion. The second thing is that the molecules are assumed to be far apart. So that means if we look at the separation between molecules, if you look at how far one molecule is from the one next to it, that's a really big distance compared to the diameter of the molecules. So they're separated by large distances compared to the size of the molecules. Okay, the third thing is when we look at the motion of the molecules, we're going to assume they obey Newton's laws of motion. So if, for instance, I want to know what happens when a molecule bounces off the wall of the container or a molecule crashes into another gas molecule, I can analyze what happens in terms of Newton's laws. So that's something we'll assume. Okay, number 4. Any sort of long-range attractive or repulsive force between the molecules can be ignored. So we know that molecules can attract or repel each other due to electrical forces between them. That's something that we're just going to ignore when it comes to an ideal gas. Okay, and the last thing is all collisions, whether it be a collision, again, with the wall of a container or a collision between two molecules, are going to be assumed to be perfectly elastic. So remember what an elastic collision means? It means there's no energy lost during the collision. So if a molecule bounces off a wall or if it bounces into another molecule, we're going to assume that it's elastic and no energy gets lost. All right, so next we're going to talk about different ways we can measure the amount of a gas. So different ways we can quantify how much gas we have in a particular sample. And we'll start with the definition of a mole. So a mole is just a way of counting things, right? It's kind of like a dozen. If I say I have a dozen eggs, I'm just telling you I have 12 eggs. By the same token, if I tell you I have a mole of eggs, I'm telling you that I have 6.022 times 10 to the 23 eggs. Okay, so that's what a mole is. It's just that many things. So the number I just quoted is called Avogadro's number. And again, it's the number of particles in a mole of a substance. So 1 mole is equal to 6.022 times 10 to the 23 particles. Now that seems like a completely random number, but there's actually a reason for choosing that value for Avogadro's number. This value was chosen so that the mass of 1 mole of a substance in grams is equal to the mass of 1 molecule of the substance in atomic mass units. Okay, so let's explain how this all works out. So the mass of a molecule in atomic mass units, or AMU, is roughly equal to the total number of protons and neutrons in that molecule. So let's explain why that is. A molecule consists of different atoms, and atoms consist of protons, neutrons, and electrons. So electrons have a very small mass compared to protons or neutrons. So basically, when it comes to the mass of a molecule, we can ignore the electrons because they don't really contribute that much to the mass. It's negligible. Also, protons and neutrons almost have equal mass. They have slightly different masses, but for our purposes, we can say they have equal mass. And that mass happens to be 1.66 times 10 to the minus 27 kilograms. And that's what we define to be an AMU, an atomic mass unit. Okay, so to give an example of this, let's consider the water molecule, H2O. Okay, so H2O consists of 2 hydrogen atoms and 1 oxygen atom. In the hydrogen atom, we have 1 proton and 0 neutrons, and also 1 electron. In the oxygen atom, we have 8 protons, 8 neutrons, and 8 electrons. But remember, the electrons have negligible mass. Okay, so in the hydrogen atom, I have 1 proton and 0 neutrons, but I have 2 of those atoms. So for the hydrogen, I get 2 atomic mass units. In the oxygen atom, I have 8 protons, 8 neutrons, for a total of 16 atomic mass units. So the total number of atomic mass units for the entire molecule is 16 plus 2, or 18. Okay? So my claim is, if the water molecule has 18 atomic mass units, then the molar mass, that's what we call this, of water, is 18 grams per mole. Okay, so let me show you how this works out. Okay, so let's start by saying that we have some kind of substance and its molar mass is X grams per mole. So we don't even want to put a number on it. Let's just say X grams per mole. And let's do a bit of unit conversion. So the first thing we'll say is in every 1 mole, we have 6.022 times 10 to the 23 molecules. Okay, and so moles cancel. The next thing we can do is convert from grams to kilograms. So we have 1,000 grams in every 1 kilogram. So do the unit cancellation of grams. And then finally, we know that in every 1 atomic mass unit is equivalent to 1.66 times 10 to the minus 27 kilograms. So we'll cancel units of kilograms. So notice what our leftover unit is. We have AMU per molecule. So if you calculate this number, it's going to end up being 1.0003 times X AMU per molecule. So what this is saying is the number of grams per mole of a substance is really, really close to the number of AMU per molecule. Okay, it's not exactly the same because it's not exactly equal to 1, but it's very close to being true that the number of grams per mole equals the number of AMU per molecule.
Right. So that brings us to the ideal gas law. It turns out there are 2 common ways to write the ideal gas law, and I want you to become familiar with both of them because we'll use them both in different contexts. So let's start at the top. We have PV is equal to capital N times KT. So let's explain what all these variables mean. So P is the absolute pressure of the gas. V is the volume of the gas. Capital N is the number of molecules of the gas. K is something called Boltzmann's constant, and the value of Boltzmann's constant is given here. It's 1.38 times 10 to the minus 23 joules per Kelvin. And then finally, T is the temperature of the gas, but we have to be very careful when we look at that variable T. T is what we call an absolute temperature, so it's in the Kelvin scale. You can only use the ideal gas law if you're using absolute temperatures measured in the Kelvin scale. It just doesn't work if you use Celsius or Fahrenheit, okay? So there's an alternative formulation given at the bottom of the page, and that's PV equals lowercase n times RT. So PV is still the pressure times the volume. That hasn't changed. But now, when we look at lowercase n, it's not the number of molecules. It's the number of moles of gas molecules. Okay? So it's just a different way of counting how many molecules we have. In this case, we're doing it in terms of the number of moles. And then R is just a different type of constant called the ideal gas constant. Let me give you the value of that. It's about 8.31 joules per Kelvin mole. And then, of course, T is still the absolute temperature of the gas. Again, we have to use the Kelvin scale. So these are the 2 formulations of the ideal gas law.
Okay, so to give you a little bit more insight into the 2 versions of the ideal gas law, the first one we saw was PV equals capital N KT, and the other was PV equals lowercase n RT. And these are almost saying the same thing. It's just whether we choose to count in terms of the number of molecules or in terms of the number of moles. So in other words, PV and T in these 2 different versions of the equation are the same. So what we can say is NK in the first equation is the same thing as little nr in the second equation. And that means R, which is our ideal gas constant, is big N over little n times K. And let's actually really spell out what that's saying. Big N is the number of molecules. Little n is the number of moles. And K is Boltzmann's constant. So Boltzmann's constant. So we can actually plug in everything we know, because let's say we had 1 mole, okay, down here. Up here we would have 6.022 times 10 to the 23 molecules. In other words, I always know the ratio between the number of molecules and the number of moles. That's Avogadro's number. And then Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. So unit-wise, what I'm left with is joules per Kelvin mole. And numerically, if you crunch these numbers, it turns out to be 8.31 joules per Kelvin mole. So that's where R comes from. All right, so I've got a couple example problems for us to try out. The first one is a gas with an initial temperature of 23 degrees Celsius is in a sealed container with rigid walls. So that means the volume can't change. If the pressure doubles, what will the new temperature be? Let's work this one out. All right, so in this first example, we'll start by writing down the ideal gas law, PV equals nRT. And then let's take a note of what's being held constant. Well, the number of molecules we have, or the number of moles, the amount of gas is not changing, assuming our container doesn't leak any gas out. The constant R, of course, is not changing because it's a constant. And then V, the volume of the container, also doesn't change because it's a rigid container. And that means it can't expand or contract. So therefore, we can rearrange the ideal gas law to say P divided by T is equal to NR divided by V. Okay, just that's a way you can rearrange the equation. But if we circle the right-hand side, we notice that N, R, and V are all constants, which means this whole thing is just one big constant quantity. Okay, so that's telling us that P over T is a constant, right? It stays the same throughout this process. So P initial over T initial, so the initial pressure divided by the initial temperature, should equal the final pressure divided by the final temperature, because again, that's a constant quantity. So we can solve for the final temperature. That's what we want. If we take the initial temperature and then multiply P final over P initial. Okay? Now, you might say we can just plug the numbers in and then go from there. But we actually have to convert units first. Remember, our initial temperature was given to be 23 degrees Celsius. In order to actually use the ideal gas law, we have to first convert this to Kelvin. So the initial temperature in Kelvin is 23 plus 273. That's how you convert to Kelvin from Celsius. And we get 296 Kelvin. So we have to use that temperature. It's not going to work if we use the Celsius temperature. Okay, so that's the initial temperature, 296 Kelvin. What's P final divided by P initial? Well, we're told that the pressure doubles, so this is a factor of 2, right? That's how we say the pressure doubles, which gives us 592 Kelvin. So if we wanted to express that final temperature in degrees Celsius, well, we would just take 592 Kelvin and then subtract 273, which gives us 319 degrees Celsius. That's the answer. But again, notice you can't just take 23 degrees Celsius times 2. That's going to give you the wrong answer. You have to convert it to Kelvin if you're going to use the ideal gas law. It's really important. And here's another example. Let's say we have CO2 gas kept in a container under 3 atmospheres of absolute pressure. The volume of the gas is 4 liters and the temperature is 155 degrees Celsius. How many particles of gas are in the container? How many moles are there?
And then finally, what is the total mass of the gas molecules?
All right, so this time, how about we use this version of the ideal gas law, PV equals capital N KT. And if we rearrange everything and solve for N, so basically divide on both sides by KT, we'll see that we have N is equal to PV divided by KT. So before we actually plug the numbers in and make this calculation, we're going to have to convert all quantities to SI. To SI units, that is. Okay? So here, let's start with Boltzmann's constant. The value is 1.38 times 10 to the minus 23 joules per Kelvin. Okay, that's already in SI units, so we don't have to do anything to that. What about the volume? The volume we were given is 4 liters. Okay, a liter is not the SI unit for volume. Do you know what the SI unit for volume is? It's a meter cubed. So we have to go from liters to meters cubed. Well, the conversion there is in every 1 meter cubed, you have 1,000 liters. And that means that we're just dividing by 1,000 to get 4.00 10 to the minus 3 meters cubed. Okay, so that's the volume in SI units. As for the temperature, we're given the temperature in Celsius. Again, that's not going to be okay if we're using the ideal gas law. We need this to be in Kelvin. So the temperature is 155 degrees Celsius plus 273 gives you 428 Kelvin. Okay, so now that's in the right unit as well. Okay, finally, let's do pressure. We're given 3 atmospheres as the unit, and an atmosphere is not the SI unit of pressure. If you recall, the SI unit of pressure is something called a Pascal, PA. How many pascals are in 1 atmosphere? You may remember that this is 1.013 10 to the 5. You can always look that up if you don't remember. Okay, so in pascals then, this is 3.0339 10 to the 5. Keep 3 sig figs on that. And let's do a closer look at the unit of pascals, okay? I'm going to show you a very useful unit equivalency that you can use. So a pascal is a unit of pressure, and I'm just going to write off here on the side that pressure is force divided by area. That is the definition of pressure. So in other words, a pascal is a force unit, which would be a Newton, divided by an area unit, which would be a square meter. Okay? But if you recall, a Newton, okay, and I'm going to write down another equation, F equals ma, Newton's second law. A Newton of force is equal to a kilogram, because that's our mass unit, times acceleration, meters per second squared, that's our acceleration unit. And then we divide that by meters squared on the bottom. Okay, I can rewrite this basically by multiplying by meters on the top and bottom. I'm going to have kilograms, meters squared per second squared on top. So I pick up an extra factor of meters. And on the bottom, I pick up an extra factor of meters, so that's meters cubed. Okay, I'm going to write down one more equation. Kinetic energy is 1/2 mv squared. So a unit of energy is equal to a mass unit times a mass unit times a speed unit squared. But that's what we have here, right? We have a mass unit, kilograms, and then we have a speed unit, meters per second squared. So this is our energy unit, which is a joule. So that was just a long-winded way of saying that a pascal is a joule per cubic meter. That's a really useful unit equivalency. You don't have to go through this whole process Again, just remember that, okay? So now we can do our calculation. Number of molecules, N, again, is PV divided by KT. So for P, we have 3.0339, 10 to the 5, joules per cubic meter. That's the unit equivalency we just worked out. V is the volume, 4.00, 10 to the minus 3 cubic meters. Divide that by Boltzmann's constant, 1.38, 10 to the minus 23 joules per Kelvin, and then multiply that by the temperature, 428 Kelvin. Now notice that joules cancel, meters cubed cancel, and Kelvin also cancels. So we're left with no units, which is exactly what we want because we're just counting a number of things. And we have 2.0546, keep 3 sig figs on that, 10 to the 23. So in other words, there are 2.05, 10 to the 23 molecules of gas. That's how much gas we have. Okay, so how about the number of moles? That's the next question. Well, if we have 2.0546 times 10 to the 23, 10 to the 23 molecules, we can convert that to a number of moles just using Avogadro's number, because we know that there's 6.022 10 to the 23 molecules in every 1 mole. Cancel molecules, we're left with moles. What do we get? 0.34118 moles. So we'd round that to a nice 0.341 mole. Okay, that's how many moles of gas we have. All right, finally, what is the mass of the gas in this container? So now we have to account for the fact that the type of molecule we're dealing with is CO2. Okay, so we have a carbon atom in this molecule. Carbon has 6 protons, has 6 neutrons, and it has 6 electrons. Oxygen, on the other hand, we saw this earlier, has 8 protons, 8 neutrons, and 8 electrons. Okay, so what's the total number of protons and neutrons? Well, in this molecule, we have 2 carbons, so each one has 6 protons and 6 neutrons. And then we have 1 oxygen, so that's 8 protons plus 8 neutrons. Again, electrons have negligible mass. Okay, that turns out to be 44. And so that means we have 44 atomic mass units per molecule. But we also saw earlier that the number of AMU in every molecule is approximately equal to the number of grams in every mole of the substance. So that means we have about 44 grams per mole if we're dealing with CO2. So the mass of the CO2 in this container, here, let's start with this. We have 0.34118 moles. That's what we calculated just a second ago. If I want to convert that to a mass, just use the fact that in every 1 mole, we have 44 grams. That's what we worked out up here. If you crunch those numbers, you'll get about 15.01 grams, which rounds off to a nice 15.0 grams. Okay, so there are 3 different ways of talking about how much gas there is. We said there are 2.05 10 to the 23 molecules, which is the same as saying 0.341 moles, which is the same as saying we have 15 grams of gas. Okay, so just know how to convert between those two ways, or those three ways of talking about things.
All right, so here's another example. And after I describe the problem for you, I'd like you to pause the video and then see if you can work this out on your own. So what's happening here is we have a cylinder which contains 3.00 mole of air molecules. The volume of the air in the cylinder is 87.5 liters. The air outside of the cylinder has an absolute pressure of 1 atmosphere. The movable piston that keeps the cylinder sealed has a mass of 175 kilograms and a radius of 12.5 centimeters. The piston is at rest. What is the absolute pressure of the gas in the cylinder in units of atmospheres? And then as a follow-up, what is the temperature of the gas in the cylinder in degrees Celsius? Remember that the pressure is defined as the force per unit area. And then I have various constants and unit conversions that you can use at the bottom of the slide. So try to work this out, see what you get, and then we'll go through it together.
All right, so the first thing we're going to do here is draw a free body diagram of the piston. So the way this works is just draw the piston itself. It's this cylindrical shape. And then label all the different forces that are acting on the piston. Well, the obvious first thing that comes to mind is the force of gravity, pulling the piston down. But there's some air inside of the piston, which is going to be pushing up on it like this. So we call that F in. There's also air outside of the piston up here, which is going to be pushing down on the piston like so. So those are the three different forces acting on the piston. But the thing is, the piston is not moving. It's stationary, which tells us that the acceleration is equal to 0. So if we now apply Newton's second law, which is F equals ma, and specifically let's look at the y direction, the vertical direction. We'll see that the net force in the y direction is m times acceleration in the y direction. So what forces do we have? Well, we have the force from the air inside the piston pushing up. That'll be considered a positive force because it's going up. We have two downward forces, which both will carry a negative sign, again, because they're in the opposite direction. So we have F in minus F out minus Fg. That's how we sum up the forces. And what we should get is 0, because again, there's no acceleration. Okay, so the next thing we'll do is remind ourselves what the definition of pressure is. Pressure is force per unit area, which means the force can be thought of as the pressure times the area. That's what we're going to use in the next step. So the force from the air inside the piston pushing up on it is equal to the pressure of the air inside the piston times the area. And then the force of the air outside the piston pushing down is P out times A. And then the force of gravity is mg. Okay? Now, remember, the first thing we're solving for is the pressure inside the piston. We're solving for P in. So I'll take P in times A equals P out times A plus mg, and then just divide through by A. You'll get P in equals P out plus mg divided by A. Okay, so that's how we solve for P in. Now, let's plug in what we are given, but let's make sure that everything is in SI units, okay? So the pressure outside was given as 1 atmosphere, but we need to convert that. In every 1 atmosphere, we have 1.013 10 to the 5 pascals. Okay, so now that is in the standard SI unit. Then we're going to add that to m times g, which is 175 kilograms is the mass. G is 9.8 meters per second squared. And then we're dividing that by the area. The area of this piston is circular. Okay, so it's the area of a circle, which is pi r squared. Pi times the radius, 0.125 meters is the radius, and we'll square it. Okay, so just to verify that the units are coming out right, in the first term, we cancel out atmospheres and we're left with pascals. In the second term, I've got kilograms, meters per second squared on top, and on the bottom I have meters squared. A kilogram meter per second squared is a Newton. That's what we have on top. And we have a meter squared on the bottom. That's a pascal. A Newton per meter squared is a pascal, so that just verifies the units are consistent. And if you crunch the numbers that I wrote down, you're going to get 1.362 times 10 to the fifth power pascals. That's the pressure inside the piston measured in pascals. But we have to convert that back now to atmospheres. So we have 1.013 10 to the 5 pascals in every 1 atmosphere. So in this unit, if you crunch these numbers, you get 1.34 atmospheres. Okay, so that's the pressure in the piston, or in the cylinder. Okay, so the last question was, what is the temperature of that air inside of the cylinder? So for that, we can use the ideal gas law. PV is equal to nRT. And we're solving for the temperature. So the temperature T is equal to PV divided by nR. Now, keep in mind, we just solved for the pressure, so we have that. The volume is given to us. The volume we were given was 87.5 liters. We better convert that to cubic meters. 1 cubic meter is the same as 1,000 liters. That's our unit conversion, which gives us 0.0875 cubic meters. R, that's the ideal gas constant. That's 8.314 joules per Kelvin mole. And N is the number of moles. We were given that, 3 moles. And then I think we're all set. So let's make the calculation. So the temperature is the pressure, which again we found up here to be 1.362 10 to the 5, and that's in units of pascals, but I already showed you that that's equivalent to a joule per cubic meter. Okay, then we have the volume, which is 0.0875 cubic meters. Then we'll divide that by nR. N is 3 moles, and R is 8.314 joules per Kelvin mole. Okay, let's take a look at the units here. Units of moles cancel. Units of joules also canceling. Meters cubed also canceling. All we're left with is units of Kelvin, which is what we expect. We're calculating a temperature after all. So this works out to 477.8 Kelvin. And the last step will be to convert that to degrees Celsius. So if we have the temperature in Kelvin and we want it in degrees Celsius, all we have to do is subtract 273. And that will give us 204.8 degrees Celsius, but we're going to want to round that off to a nice 205. Okay, so it's 205 degrees Celsius That's the temperature inside of this cylinder. Okay, so that's it for this lecture. Before I wrap the video up, I just want to point one thing out to you. At the end of all of my lecture slides, which again, you can see on Canvas, I have practice problems. So these problems are just problems that I made up. They have to do with the material covered in the lecture. And you can do these at home as practice, as a way of studying for things like tests. These are not assigned. You never have to do these and turn them into me or anything like that. These are just here for you to study with, okay? So the answers to these problems are also posted to Canvas, so you can do these for practice and then see that you're getting the right answer. So that's just a tool that you can use for studying, okay? Just know that it's here. We don't have enough time in this video to go through any of these, so we'll end it here. I'll see you in the next video. Until then, take care.